Okay, so we're starting section 4.2, talking about entropy, and then later we're going to talk about free energy in the next video. Today's video we're concentrating on entropy. It's just the first side of the first page of this unit. So I've gone ahead and wrote a lot of this down so I can speed up the video. And most of this is already written down. It's not until we get to the bottom that you have to even write anything. So here's what it says. Thermodynamic quantities are generally reported as a standard state. And so standard states has a handful of conditions, and it depends on what state of matter you're in. So for an aqueous solution, looking at this one, the concentration of a standard state would be 1 mole per liter. If your substance is a gas, its standard state assumes that you have a partial pressure of 1 bar, which is approximately 1 atmosphere. Temperature for standard state is 25 degrees, or if you're in Kelvin, it's 298.15 Kelvin. And if you're talking about a reversible reaction, Q equals 1. So these are the requirements for your standard states. So when you have something that's in a standard state, their symbols look just a little bit different. And so if you look here, I have standard compared with not standard. And the only difference is this little degree sign that's referred to as a not. So delta H not. We would just say here the standard change in enthalpy for this one. This H is enthalpy. Write that in. H, delta H, we've already talked about it in 4.1. It's enthalpy. It has to do with heat. It has to do with the amount of heat exchanged in a reaction. This concept will come back, but it doesn't show up a whole lot in this section. It does in the next video. Delta S, standard state, and then you've got some others. This is just for a comparison between standard and not standard. You really don't need to write it down. So entropy is denoted by the symbol S, capital S. So there's a couple definitions, and there's maybe more if you look on the internet. One definition, in the notes it says the number of arrangements of particles. And I added the word possible, the number of possible arrangements of particles. So this is saying how many different ways can you move around the pieces that you have. Could also be known as the disorder of a system, or how unorganized is it, how messy can it get. And in general, the messier it gets, the better in chemistry. The more possible arrangements, the better it's going to be. So absolute entropy is a number, and you'll find it in data tables. And so whenever you have a substance, it's just automatic, like this substance in this state has a specific number for entropy. And in general, a more complex substance will have a larger value for S. A more complex substance just means that it has more possible arrangements. Entropy change, or delta S, is where we really want to concentrate our efforts here. And so we're looking at the change in entropy, or the change in the number of possible arrangements, the change in the disorder of a system. And so we want to know about delta S. So when delta S is greater than 0, meaning that delta S is positive, entropy is increasing. Basically, the system is becoming more disorganized. When delta S is less than 0, entropy is decreasing. It's a negative. Delta S is negative. And the system is becoming less disorderly. So imagine that you're in a room. If you start cleaning the room and picking things up off the floor, putting books back on the shelf, putting clothes in the laundry basket, the system is becoming less disorderly. So if you're cleaning a room, you're tidying up a room, basically the entropy is decreasing. This is kind of a crude analogy. If you go into a room that's fairly clean and you start throwing magazines on the floor, dumping out the clothes hampers, pushing pencils off the desk, the room is becoming more disorderly, and your delta S will be positive. There is a formula on the AP formula sheet, and it's here at the bottom. Delta S equals the sum of the entropy of all of the products minus the sum of the entropy of all of the reactants. You'll see an example of this towards the end of the video. There's a second way you can calculate delta S, and this is using Hess's law. So we've had this idea of Hess's law before. It's where you have two, maybe more reactions, and you are putting the reactions together, and you're also putting this value together. So for Hess's law, we've done it with enthalpy. So when you put two chemical reactions together to make one big chemical reaction, you are also adding the delta H's together, and it's the same idea here. There's a handful of ways that you can increase the entropy of a system. Changing or increasing the entropy, we're talking about a delta S that is positive. It's greater than 0. Number one, increase the temperature. If you heat something up, things are moving faster. The particles have a greater kinetic energy. It's going to be more disorderly. There's more possible arrangements. If you increase the volume of a gas specifically, so if you have a small container of a gas, the particles are somewhat limited in where they can go. But if you put that gas into a much larger container, there's just more places where those gas particles could go. So increasing the volume of a gas. Number three, increasing the moles of substances. And if you look here, we have 2 ozone gases becoming 3 oxygen gases. The moles of the substance in the reactants is 2. And in the products, the moles is 3. And so we have increased the number of moles of all the substances, and therefore we have increased the entropy. Number 4, you could increase the number of substances that you have. And so we have the reverse reaction of the Haber process. 2 ammonias, and it's decomposing into nitrogen gas and 3 hydrogen gases. So we went from having 1 reactant to 2 products, and that's one way to increase the entropy. If you look at this one another way, we have also increased the number of moles. There are 2 moles here, and there are 4 moles of product. And so there's actually 2 things going on here. Number 5 is changing states. So a solid has the least entropy. A liquid would have more entropy, and a gas would have even more entropy. Number 6 is changing a pure substance to be in a mixture. And the example here is we have solid potassium bromide, and we are dissolving it in water, and there's just more ways that you could arrange this potassium bromide. If it's in a solid, it's relatively still. The particles can't really move around. But once you dissolve it in water, everything is free to move around a lot. And so entropy has increased. Example 1 says, predict if the change in entropy is positive or negative. In part A, we have a solid calcium carbonate becoming a solid calcium oxide plus CO2 gas. And so thinking about the rules that are directly above on your paper, we have the reaction forming a gas. So this has a pretty low entropy, and this has a pretty low entropy. But we also have a gas now in the products. And so remember, gases have a greater entropy. So the delta S is positive or greater than 0 because the reaction forms a gas. In part B, we're looking at iodine. It's changing from a gas to a solid. So the delta S in this case, it is going to be less than 0 because we had a gas over here which has a lot of entropy turning into a solid which has less entropy, and so it ends up less than 0. System gas to solid. Part C, we have methane plus 2 oxygens yields CO2 gas and 2 liquid waters. And so the change in entropy. So let's look at a couple different things. So temperature, we don't know. Volume of a gas, we don't know. Increasing the moles of a substance in the reaction, that was 3 and 3. Increasing the number of substances, it was 2 and 2, no. 5, changing states from solid to liquid to gas. So here we have 3 moles of gas basically, and over here we only have 1 mole of gas. The liquid has a lower absolute entropy, and so delta S is less than 0. Say fewer moles of gas and products. Part D, we have 2 NO2 gas yielding N2 gas plus 2 O2 gas. So with this one, first off, we have the number of substances increasing from 1 to 2. So that's going to be an increase first off. So it's going to be positive. We also have more moles of a gas in the products and the reactants. So that agrees with this assessment. Delta S is greater than 0. And so let's say so the products have more moles of gas than the reactants. In example 2, we're putting some numbers into here. In part A, same idea as last time. Predict whether the change in entropy will be positive or negative for the reaction above. 2 SO2 gas plus O2 gas yielding 2 SO3. So let's go down the list. Temperature, don't know. Volume, I don't know. Increasing the moles of a substance in reaction, no. So we can guess that it's probably going to decrease, which means less than 0. If we look at the next one, increasing the number of substances in reaction, no, we didn't do that either. And so definitely negative. Changing states, they're all gas. And so we can predict pretty well that delta S is less than 0. It's going to be negative. But here we can also put some numbers to it. We want to calculate the standard change in entropy given this table of absolute entropies. And this is where the formula comes in from the AP formula sheet. Delta S equals the sum of S of the products minus the sum of S of the reactants. And so let's look through our numbers here. So first off, the products, we have SO3. So we have to consider something else. There are 2 moles of SO3 in the reaction. That's from the coefficient of the balanced equation. And then here we have, for SO3, 257, and that is joules per mole per Kelvin. Moles cancels out. And that's it for the products. And then so we subtract out the reactants, and we have 2 moles of SO2, 248 joules per mole times Kelvin, plus, let me move this up, out of the way. That almost worked. Plus, we have 1 mole of oxygen, and it is 205. Again, canceling moles. So the standard change in entropy we have, let's write it a little bit cleaner. 2 times 257 minus, we have 2 times 248 plus we have 1 times 205. And it should come out, a standard change in entropy is negative 187, and that's joules per Kelvin. And just like we predicted, it is less than 0. And remember, less than 0 means entropy decreases and the system is becoming less disorderly. There's going to be fewer possible arrangements for the products compared to the reactants.